Now we're going to look at chemical equilibrium, and I just want to tell you how we're going to go about doing this. We are first going to look at the conditions that's needed for chemical equilibrium. Then we're going to look at the definition, and we're going to look at a few questions, and we're also going to look at how you apply Le Chatelier's principle, what Le Chatelier's principle says, and how we apply it. And for that, I'm going to use quite a few questions, reactions that came from question papers that I'm going to do on the page so we can illustrate how Le Chatelier works. So back to our slides. The conditions for equilibrium and the definition of chemical equilibrium. So first of all, it must be a closed system. There can be no equilibrium if we do not have a closed or isolated chemical system, because if it's open, we can find that some of our products can disappear. And secondly, the reaction involved must be a reversible reaction. You cannot have equilibrium if we do not have a reversible reaction. The definition of chemical equilibrium is that if in a chemical system, the rate of the forward reaction is equal to the rate of the reverse reaction. And what is important is the word rate that need to be repeated twice, because many times learners say if the forward reaction is equal to the reverse reaction, and that is incorrect. The forward reaction can never be equal or identical, but the rate of the forward reaction can be equal to the rate of the reverse reaction. We're going to look at Le Chatelier's principle, and we are going to look at applications. So we can now go to our page. So we say Le Chatelier, so this is how we spell it. And the conditions is, number one, we must have a chemical system at equilibrium. I'm going to shorten equilibrium like that. We obviously know it must be a closed system. And the second thing for Le Chatelier to kick in or to be applicable is that there must be a change in conditions, or we can say alternatively, there must be a disturbance of the equilibrium. So the conditions that we're talking about would be temperature, it could be pressure, and it could be concentration, so Le Chatelier becomes effective if first of all we have a system, a closed system at equilibrium, and then somebody changes the temperature or the pressure or the concentration of anything in there. If we talk about concentration, this could be concentration of a reactant, or it could be the concentration of a product by removing a product because we need it. And then if we have to put that all together, we say, if I come to number 3, the system will adjust to counter the change. So if we give the definition in terms of the change, we say the system will adjust to counter the change. But countering the change would also be to restore the equilibrium. So if there was equilibrium in a closed system, and then there's a change in the conditions or a disturbance of the equilibrium, the system will adjust itself to restore that equilibrium or to counter that change. Now we said before, we must have, let's say we put a hypothetical reaction, and we say for equilibrium it must be reversible, and that's our symbol, and we get the product AB2. Then we find that there's only 2 ways that this system can in fact adjust, and that is by favoring, number one is, it can favor the forward reaction, or it can favor the reverse reaction. So when we talk about the Chatelier, we try to see what will happen. How will this thing restore the equilibrium? Will it make more of AB2, or will it go back and reform A and 2B? And what we're going to do next is I'm going to use a diagrammatic manner in which I would like to explain to you how to understand the Chatelier's principle. Just want to explain quickly. The sketches I'm going to use now are sketches that I use personally to bring across the concept of Le Chatelier. So it is not something you'll find in another textbook, and I hope that you will give comments if we and let me know whether you like it or not. I see there's a question. It says there, is it wrong? It's a question from Shawnee. Is it wrong to say the equilibrium will shift to cancel the change? I think it's a general way that we explain it, and like I mentioned now, we can either favor the forward reaction or we favor the reverse reaction. So what we say, if we had A plus B to B, that would be my forward reaction. So shifting to the right is sort of a general, I can't call it slang, but it's a way that we in chemistry indicate that the forward reaction will take place faster than the reverse reaction. So this is faster. That means shift to the right. On the other hand, if we find that AB2, the product, forming the two reactants again, if that is faster, in other words, we say the reverse reaction is favored, then we call that shift to the left. So the idea or the expression of shifting to the left or to the right to restore the equilibrium, I think it's widely accepted, but it basically would mean that shifting to the right is when the forward reaction is favored, and shifting to the left is when the reverse reaction is favored. So I hope that answers your question, Shawnee. And now we're going to go to our diagrams. I'm going to make a small circle, and I'm going to call this my system. And I'm going to make a rectangle around it, and I'm going to call that my environment. And this system would be my reactants and products colliding and reacting, and at equilibrium we find that the forward reaction and the reverse reaction will be exactly the same. If I now come with a notation for this specific reaction that delta H is less than 0, which means I'm working with an exothermic reaction. Then with my notation, this means that while this equilibrium is established, all the time the forward reaction gives energy to the environment, and the reverse reaction takes energy from the environment. So that's an inward arrow and an outward arrow. And at equilibrium, we find that these two happen at the same rate, and therefore the temperature in the whole system and environment remains exactly the same. If I now come and somebody decreases the temperature, in other words, I'm going to make an outward arrow from my environment, so there will now be a lack of energy or a lack of temperature around the system. Then according to Le Chatelier, the system must do the thing that will replace that will counter that change. And if you look at these two arrows, the only way the system can replace that energy that has been lost to the environment is when it favors the forward reaction. So I'm going to repeat what I said. The circle represents the system, which is my reactant, my product, molecules and particles, colliding all the time. And forward reaction means product is formed. Reverse reaction means reactants are reformed. For this specific reaction, delta H is negative, which means I deal with an exothermic reaction as my forward reaction. And that is the notation I just want to make clear. If I have A plus 2B and I get AB2, and for this reaction I say delta H is negative, then it means forming my product is exothermic, but reforming my reactants is endothermic. And many times people get confused because the delta H is written behind the full reaction, but it is applicable to the forward reaction, and the opposite is applicable to the reverse reaction. So if I write that out, then I say A plus 2B going to AB2 is exothermic, but AB2 going to A plus 2B is endothermic. And that's very important to understand. I'm going to go back to my example, and I'm going to say, if you look at the black arrows, I say that while equilibrium is there, then the forward reaction will release energy or heat to the environment, while the reverse reaction will take energy from the environment. As soon as I come with a disturbance by taking energy out, according to Le Chatelier, the system will do the only thing it can do to counter that. In other words, it will put energy into the environment because the disturbance has been to take energy out. And I hope I'm going to get a few comments as to whether you understand it or whether you would like me to do another one, or maybe shall just do another one with a different reaction. So again, I'm going to have my system, and I'm going to have my environment, and this time I'm going to say delta H is positive, and that means I have an endothermic reaction. So for this reaction, I see that my forward reaction, this is my forward reaction, takes up energy from the environment, and my reverse reaction gives energy to the environment. So what I will do now as my disturbance, I will say, if I now decrease the temperature, in other words, if I take energy out, decrease temperature, then according to Le Chatelier, this system must favor the reaction that will put it back into the environment, and that will be my reverse reaction. So therefore, for this question, which reaction will be favored if the temperature is decreased? The answer will be the reverse reaction will be favored. And as Shawnee has asked, can we say shift? We say the equilibrium shift to the left. I think there's another question. Can I say it moves to the opposite side? And that's from a visitor. I think what I normally tell my learners in a grade 12 or 11 class is that we don't want to be snobbish as scientists, but when we give an answer, our answer must be as close as possible to a scientific answer, and our answer must be at the level of a grade 12 learner. So somebody in grade 9, maybe grade 8, who has never done Le Chatelier, who don't know about reversible reactions, and we don't know about shifting of equilibrium, they will say it will go to the opposing side. But I think for ourselves it is appropriate, and it's just the right thing to say that the equilibrium will shift to the left, because you also have to specifically say whether the forward reaction is favored or the reverse reaction is favored. So we can't say it goes to the opposing side. You have to say shift to the left, shift to the right. Forward reaction favored or the reverse reaction favored. So what I'm going to do now, I'm going to take a specific reaction and apply Le Chatelier's principle to it, and also then apply this little principle that I illustrated to you on the sketches now. Okay, so in this reaction we have sulfur dioxide reacting with oxygen to form sulfur trioxide. It's my forward reaction. My reverse reaction is sulfur trioxide dissociating to form sulfur dioxide and oxygen. As you can see, I've indicated in red that the forward reaction is endothermic. I've used the symbols delta H less than 0 or delta H negative, which indicates that the forward reaction is exothermic. And now I'm going to write in a disturbance, and my disturbance will be that I decrease the temperature. So that has been a system at equilibrium, and here I come with a disturbance. And immediately it means that the system is no longer at equilibrium. But we've got our friend Le Chatelier that says that this system has the ability and it will adjust itself to counter that disturbance. So the first thing we say, if the temperature was decreased, my system must favor the reaction that will increase the temperature. In other words, according to Le Chatelier, and I'm just going to see, the system must favor the reaction that will increase temperature. And then we look at our reaction and we see that the forward reaction is exothermic. In other words, the forward reaction gives off heat. The forward reaction increases temperature, and therefore the forward reaction will be favored. Or the equilibrium will shift to the right. And that is how we apply the Chatelier's principle. So what we're going to do now is I'm going to give you another disturbance for the same reaction, and let's take a different reaction, and then I'm going to leave it to you to answer the question and send through your answers, and just for me to see whether you are with me on how Le Chatelier is applied for temperature change. There are specific things to look at when we talk about pressure, but I think we're first going to give you a little bit of work to do. And this is Old Faithful, the formation of ammonia, when nitrogen reacts with hydrogen to form ammonia. And this is also an exothermic reaction. And my disturbance is that I now increase the temperature. And many times in the exam, it will be you will be told at equilibrium at 500 degrees Celsius. And what I'm going to say, my disturbance will now be that I increase the temperature to 600 degrees Celsius, and I'm going to give you a few minutes to give me some answers back as to what will happen according to Le Chatelier.